most of us are new objects. Some of the tools are also new. So we have to be super cautious about every single thing here, especially because we're dealing with both vectors and scalars. Right? So every time we're dealing with this, we have to be super cautious. You have to be careful about the object you're computing, whether it's a vector or scalar. In the end, you're supposed to get a vector or you're supposed to get a simply number. So the definition of a vector is given by a vector field is given by I usually denote a capital F with a small arrow here. So this is F of x1, G of x1, where F and G are scalar functions. Right? So putting every pair of x, y, I'm supposed to get an x component determined by F, small f, and a y component determined by small g. So this guy can also be written down in a slightly different form. So in last lecture, we graphed several different vector fields, right? So we put the formulas in, for instance, f is equal to 2x to y. We put the formulas in, we plug in a whole bunch of points, and then at every base point, we find the vectors according to this formula, and then we draw a family of vectors, right? And for some special vectors, we also see some geometric feature of them. This one is called a radial vector. We also have rotating counterclockwise vector, right? And these two vectors are particularly interesting, not only for their geometric features, but also we mentioned about a property. This vector is the gradient vector of a scalar function, right? So we found this parent function, or mathematically speaking, a potential function, okay? So we actually find a small f, but I want it to be different with the component defining the x component function. So let's use the phi function. Phi function, which is equal to x squared plus y squared, where this vector field can be written as a gradient vector field of a scalar function, all right? So I have a scalar function x squared plus y squared. I take the x component derivative, I got 2x, y derivative is equal to 2y. So this vector is not only interesting in its geometry, right, in its picture, in its graph, but also it has a very special property that it can be written as a gradient vector of a scalar function, right? This is a very, very important fact. And this kind of vectors will be called the conservative vector fields, which we will spend a majority of time to discuss today. Whereas second vector, it cannot be written as a gradient vector. No matter what scalar function you give me, there's no way this guy can be equal to the gradient vector of that scalar function you give me. In other words, there's no scalar vector, no scalar function, such that this function is equal to the gradient. So this one is not a vector or gradient vector. Gradient vector. So one of the first things I want you to keep in mind is the following. There are so many different kinds of vector fields, right? So every time I give you a pair of scalar functions to define x component and y component, you're getting a vector field, all right? There are so many vector fields, only a few of them are conservative, okay? So first thing you have to learn about vector fields is that there are a great deal of vector fields. Some of them are conservative, some of them are not. So one of the most important jobs we want to do is to determine a given vector field, whether it is conservative or not, right? So this is the very first job we have to do, whether it is conservative or not. If it is conservative, can we find the potential function or the parent function? How do we find that? So this is a very realistic problem we have to solve. We also talk about the so-called line integrals. So this line integral is with respect to, strictly speaking, is a curve integral, because we're given a curve, which is defined by a vector function given by, I want to write it, xt, yt, where t goes from A to B. All right? And we also discussed the several very popular parametric equations of different curves. For instance, if I have RT is equal to cosine t, sine t, this parametric equation defines a circle. And by changing the domain of your parameter t, you can make it a whole circle, a half circle, a quarter circle, 2 rounds of circles. It's up to you, right? So you can change this parameter range to get different pieces of the unit circle. We can also define the parametric equation for generally an ellipse. Right? So t goes from 0 to 2 pi will give you a whole ellipse. And we also talk about this kind of parametric equation. If x is equal to t, y is equal to t, what does this parametric equation do?
It's linear.
A very easy y equals x.
Excellent.
So this actually defines y equals x. So we actually discussed about the relation between this kind of usual equation we discussed before and this parametric equation. I can eliminate this parameter easily. Eliminating these kind of parameters, I use x squared plus y squared is equal to 1. Eliminating this parameter is even easier. I have x equals t, y equals t, so x has to be equal to 1. All right? So more generally, if I have a straight line given by slope m, y-intercept 0b, how can I translate this into a parametric equation? How can I translate it into a parametric equation? If you want to write down a parametric equation, you have to have a parameter, right? In other words, you have to introduce this new variable t to let it mean something. What do you want the t to denote here? You can let t to denote y, but then you have to solve for x. The easier one is I just let x to be t. So x is equal to t, y is simply mt plus b, right? So you just need to introduce a parameter, and this parameter you choose is going to give you a parametric equation where you have to find its relation with x and with y, right? So you begin from the easiest relation. I just make it x equals t, and y is simply mt plus b. So this is how you translate the general equation into a parametric equation, okay? There is another very popular parametric equation for straight lines. So if I have a line passing through x0, y0, and parallel to the vector AB, okay? So I know if it passes through a point x0, y0, and I have a direction AB as a vector, then I will have a whole straight line passing through this point, parallel to the vector here. Do you agree with me? These two pieces of information will uniquely determine that straight line. All right? So you have a point, and then I have a direction. That will determine a line. All right? So if I have this information, how do I put down the parametric equation? We actually talked about this in the very beginning. What's the parametric equation look like? x0 plus at, y0 plus bt. Okay, so this will be the parametric equation for a straight line with these two pieces of information. When you let t equal 0, it is exactly going to pass through x0, y0. If t goes from 0 to infinity, then this point moves from x0, y0 to the positive direction of the vector, the same direction of the vector. If you let t to go from 0 to negative infinity, it's going to go to the opposite direction of the vector. You see that? So the parametric equation gives you the curve, but also gives you the orientation, right? So that's what is orientation thing. If t goes from 0 to infinity, it's going to go in the same direction of the vector, beginning from the initial point. If t goes from 0 to minus infinity, then it's going to go the other direction. Okay? Or you can change your range of t from 0 to 1, from 0 to 2, then that will give you pieces of straight lines. Are you with me? So this is the thing. I also mentioned we will be able to generalize these vector fields from 2-dimensional to 3-dimensional. The only thing you need to add in is one more So I'm gonna keep my work a little light. So hx1. So this will be a vector field in R3. And I can write it in the form of, oh, sorry, because I have 3 variables. So these components are all going to be depending on 3 variables, x, y, z, x, y, z, x, y, z, x, y, z, and h, x, y, z. Okay, so I have 3 components. 3 scalar functions depending on x, y, z, and we can also talk about conservative vector fields. So conservative vector fields can be also written down as a gradient. I give you the simple radial vector field in R3, right? So where phi has to be equal to x squared plus y squared plus z squared. Okay. So this vector field is a very special vector field because it is the gradient vector field of this scalar function. So I take the x derivative, y derivative, and z derivative. Okay. So today we'll be able to not only discuss conservative vector fields in R2, but also in R3. So in R3, the problem is the same. Given any vector field, how can we determine whether it is conservative or not? If it is conservative, how do I find that particular parent function? But before that, I want to mention a couple of more examples on these line integrals. They even cover, I think, sufficiently many. So line integral is given by C, F, and Bx, okay? Where C here is determined by RT. So let me see what my example is. So if I have a vector field, if I have a curve which is from the line segment from 0, 0, 0 to 1 to 5, and also my f of x, y, z is equal to x times y times z. Okay? So I want to compute the line integral. Every time if I want to compute a line integral, I have to have 2 objects, the line and the function. Right? So I have to have a function to take the integral. Because it's a line integral, I have to have a, strictly speaking, a curve. This curve is indeed a line. It's a line segment from 0, 0, 0 to 1 to 5. And the integrating function I'm looking at is x, y, z. First of all, we have this formula. We have this formula to translate this line integral to an integral involving the parameter t. All right? So it is an integral from the initial time a to terminal time b, where I have to change everything here into xt times yt times zt, because this integrating function is x times y times c. All right? And then I have to multiply by the length of this segment element. Right? So this is the arc length segment. Are you with me? Remember, when we compute the line segment or the arc length of a line, we actually integral without this part, right? We just take the integral of this component. Okay? So if we're taking the line integral of a function, we need to stick in this function right here. Regardless of what formula you're using, we have to get the parametric equation of the line. All right? That's the initial step we have to go. Regardless of what formula you're using, as long as you're taking anything with respect to a curve or a line, you have to get a parametric equation of that line. This line is going from 0, 0, 0 to 1, 2, 3, and then it's a straight line. I know the equation should look like this one. All right? Mm-hmm. The equation should look like x0 plus at, y0 plus bt, and z0 plus ct. So z0 plus ct. Okay? So I can easily choose one of the points here. 0, 0, 0 is the initial point. So I want to have x0 to be 0, y0 to be 0, z0 to be 0. All right? Then I need to find a, b, c as the vector is parallel to. And this one is parallel to a vector of these 2 points. Am I right? If I line these 2 points together, this is going to be a vector that is parallel to this line right here. So easily I can find the vector to be 1, 2, 3. So this, I'm sorry, 1, 2, 5. This parametric equation is going to be super easy. It's going to be t, 2t, and 5t. Okay, that was me. T, 2t, and 5t. You can easily check this. You can easily check this because for a line, 2 points will determine uniquely a line. T equals 0 will pass through 0, 0, 0. Am I right? T equals 1, this it will be passing through 1, 2, 5. All right? So this is indeed the line passing through these 2 points. Are you with me? Anybody else? Yeah? Not only I can check it passed through these 2 points, I also checked the initial time and terminal time. Right? Because every time if I have a parametric equation, not only I have to have these equations, but also I have to have the range of the parameter. All right? Going from 0, 0, 0 to 1, 2, 3, t goes from 0 to 1. Okay? So I have to be able to not only determine these 3 components, but also this is super important. You have to be able to see where it begins from and where it ends at. Because these 2 points is going to be these 2 numbers. All right? These 2 numbers. You have to be able to figure out what the equation like and what's the initial time and terminal time is. Okay? So this is going to be from from 0 to 1, xt is equal to t, yt is equal to 2t, zt is equal to 5t, and this length is equal to square root of x prime squared plus y prime squared plus z prime squared. Am I right? So this is essentially my x, this is essentially my y, this is essentially my z. So x prime is equal to 1 squared plus 2 squared plus 5 squared then dt. That was me? So as long as you can find the parametric equation with the formulas as well as the initial time and terminal time, the integral itself is a single variable integral with respect to parameter.